Our next session, this afternoon's session, is about the technical aspects. And up next is Brian Majka. He'll be talking about understanding how waves work. Brian is with GEI Consultants and was a co-author of the Michigan Natural Shoreline Partnerships Contractor Training Manual. And he was also one of the founding members of our partnership that began in 2008. He has been working on this topic for many years and is always a treat to listen to Brian speak. So with that, I will turn it over to Brian.
Thank you, Julia. I will go ahead and get started then. I apologize for the technical difficulties there. So this afternoon, we're going to talk a little bit about waves. You could probably subtitle this talk, Waves for Non-Engineers, in part because I myself am not an engineer. I'm a restoration ecologist, but what we're going to talk a little bit about is some of the mechanics of waves, how they work, and specifically how those waves interact with shorelines. So we'll talk a little bit about what waves are, where do waves come from, some of those characteristics, how do waves impact shorelines, and then we'll talk a little bit about wave energy assessments. Again, we're going to talk about the mechanics of how waves work and how they interact with shorelines, but we're not necessarily going to get into any kind of detailed calculations or modeling or anything like that. But it is important for people working with shorelines to understand some of the basics of waves, where they come from, and how they can ultimately affect and impact our shorelines themselves. So you heard John Hardig use this term, and it's one that's really important when we're talking about our shorelines. We call it the land-water interface. And this land-water interface is a very narrow habitat niche. In some places, it can be just a few yards wide even. But the land-water interface is incredibly important ecologically because that is the zone where a lot of our wildlife specifically needs to pass back and forth between the land and the water. And what makes this area especially tricky is that this specific zone is especially susceptible to erosive forces from waves. So start out with a basic definition. What is a wave? So a wave is a swell in a body of water, typically with some kind of forward motion. Something that's really important to keep in mind with waves is that a wave is not an actual transfer of matter itself. Wave is a transfer of energy. So I saw this quote, and I can't remember where it came from, that wave energy is essentially just a form of solar energy. Because what happens is the sun heats the earth, that heating, differential heating creates wind. And then that wind energy is then transferred to the water. And as that energy is transferred to the water, it creates this wave energy. But the interesting thing to think about and always keep in mind is that a wave is not necessarily a transfer of matter. So if you think about it, if you're out in a lake sitting on a raft on a windy day, one wave itself does not necessarily push you all the way into the shoreline. Instead, you wind up bobbing up and down as those waves pass you because that energy is passing you, but the actual matter, the actual water itself is not actually moving all the way into the shoreline. So it's important so that we're all on the same page here, that we start out with a few quick definitions. Sometimes as we're talking about these things, especially with the audience size that we have, understanding that everybody comes from different backgrounds, it's important to kind of set the stage with some definitions. And the first one here is fetch. When we're talking about wave energy and shorelines, we talk about fetch all the time. And the fetch is essentially the longest uninterrupted distance across the open water from a site. So here in our example, this is Mullet Lake up in northern Michigan. If the star is our shoreline itself, you can use a simple tool like Google Earth and draw the distance and find the longest possible reach to that site across the body of water. And we call that the maximum fetch. In this case, it's about 7.5 miles. We'll talk about why that's important a little bit later. But what's important to know is just that term fetch, which is the distance across a body of water. The next one we talk about is wave run-up. And a wave run-up is the quote unquote maximum onshore elevation reached by a wave. So what that means is as a wave moves closer to the shoreline, eventually that wave will break. How far onto that shoreline is that energy transferred? Is that water moved? Because ultimately that's going to give us an idea of what reach of the shoreline might need some kind of protection. Bathymetry. The bathymetry is the elevation of the bed in a body of water. So bathymetry is essentially topography, but underwater. And then the last thing we're going to talk about is slope. And slope is described in terms of run to rise. So when we're talking about shoreline slopes, sometimes you'll hear people talk in terms of degrees and things like that. But a very common way that we phrase shoreline slope is we might say 5-to-1 or 6-to-1 or 10-on-1. And what that means is you have 5 essentially feet of or any other unit of run to 1 foot of rise. And you can see in our graphic here on the lower right how that comes about. What that means is that a 1-to-1 slope is going to be a very steep slope because you have 1 foot of rise for every 1 foot of run. And a 20-to-1 slope is going to give you 20 feet of run for every 1 foot of rise. That's going to be a much gentler slope. And we'll go into much more depth about why slope matters so much when we're talking about waves and shorelines and shoreline protection just a little bit later. So where do waves come from? We really see 3 main places where waves are derived. One being wind-driven, the other being gravitational, which is essentially our tides, which, you know, for the most part here in the Great Lakes, we don't have to worry about that. So we're not going to talk about that too much. And then there's also disturbance-driven waves. And these are things like tsunamis, or most commonly, in something that's talked about a lot today, boats, or you can think in terms of a cannonball. If you jump off a diving board and into the water, you are creating waves through that disturbance or that displacement of water. But really what we tend to focus on most when we're talking about our lakes and shorelines and shoreline protection are wind-driven and those disturbance-driven or boat-driven waves, which we're going to talk a little bit about more now. So I talked a little bit ago about how waves form and how that energy is transferred from the wind to the water. Well, what happens is anytime there's movement between 2 objects, there's friction that's created. So if you think about a very calm day, a very calm body of water, and a very light wind, there is, as that wind blows across the water, there is some friction that's created. If the wind is very light, has very low energy, though the amount of energy transferred to that water body might barely even be noticeable. But as that wind picks up and there's more energy created, the friction of that wind passing the water starts to create ripples. That friction creates movement in the water itself. And you get what we call these micro ripples, kind of what you see in this photograph here. Well, what happens is this effect starts to multiply on itself. So if you have a stronger wind, those micro ripples start to turn into larger ripples because those micro ripples then have a rougher surface, which then creates more friction. So as that wind then continues to build, those ripples get larger and you get more friction. And then as the ripples get larger, you get more friction. The ripples get larger, you get more friction. And those ripples start to really turn into waves. So what we see with wind-driven waves is that the wave is really a function of the speed of that wind, the distance that wind travels across that water body, the fetch that we talked about to begin with, and then also the duration, because the longer that wind blows, the more time there will be for these waves to build. So this is an example of some of these wind-driven waves that we see. So the wind's going to have a direction, and then the waves that start to form and build out of that, you're going to have a wavelength. And the wavelength is going to be the distance between the 2 crests of those waves. And then one of the other physical characteristics that you're going to see forming these waves is the wave height. And the wave height is going to be the difference between the crest and the trough of a given wave system. So what happens with these wind-driven waves is the wave starts to move toward the shoreline. Then as you get closer to the shoreline, that wave is going to start to break. A key factor as a result of that, or key physical factor, is that the waves are going to start to break and lose energy when the wave height reaches approximately 80% of the water depth. So what happens is all of that energy is transferred to the water. As that wave energy starts to come closer to the shoreline, that energy you're going to have friction not only at the surface, but that friction is going to start to interact with the lake bed itself. And that's going to cause the wave to rise up and start to crest over. And that's where at that point you get what we call this swash and backwash, or backswash, you might hear people call it. So when you're talking about energy interacting with the shoreline, you have the orbital force of that wave breaking, and then you have that swash and backwash interacting with the shoreline itself. And you can see all of that pretty clearly in this video. So in addition to wind-driven waves, something that we're typically very concerned with are boat-driven waves. So boats create a disturbance in the water. They displace the water as they move. And the size and shape of the waves that are created are going to be influenced by the hull and speed. Now, something that we're seeing that's becoming a very common problem, and Alex is going to talk about in depth after I finish up here, is wake boats. Because when we're thinking in terms of shoreline protection, we're thinking we want the smallest waves possible, right? Well, wake boats are specifically designed through their shape and their hulls to actually create larger waves. So, and in these cases, boat-driven waves can actually be larger than what wind-driven waves can actually be. And that's because the boat-driven waves, as opposed to being limited by water depth or fetch or wind speed, boats can actually be designed to push water up. And when that happens, these boats are actually designed to create larger waves. So something you see and something that comes into place a lot when we're talking about things like no wake zones and things like that is that the wave height actually starts to get reduced when a boat starts to plane. So this is something so what happens is a boat starts to move. It's moving water. You might hear the term plowing water. As that boat speed starts to pick up, and you can see it in this graph here, wave height's going to go up and up and up and up. But then once that boat starts to hydroplane across that body of water, the wave height actually starts to get reduced because that boat is essentially hydroplaning across the surface of the water, and it's displacing less water at that point. So what we've seen on some different shorelines happen is when people are setting no wake zones and buoys and things like that, some of the most erosive forces are coming right around those no wake zones where they stop and start, because that's where boats will start to plow water or come down off of planing and actually plow water, to use that term, and push more water up right at or just inside the no wake zone as opposed to outside the no wake zone. So these are things that are important to keep in mind with boats. And one of the other characteristics to keep in mind with boat-driven waves is that even though the waves are periodic, they're typically going to have these longer periods, and you can get these longer wave heights. So I actually took this video this past Monday. We were on a 16-foot flat bottom boat, and this is out on Lake Erie, and we weren't going terribly fast. And you can see this relatively small boat that we were on, just how much wave energy is being created. It might take a 30 to 40 mile an hour wind to create waves this height in the specific water body. In this case, a relatively small boat is able to create a fairly large wave. And this is a boat that wasn't even designed for creating waves like wake boats are. An important thing to kind of take away from here, and this is something that, has kind of become a personal hobby of mine, is just watching waves and watching how they form, how they break, and how they interact. And you'll see as you watch this video and compare it to the wind-driven waves that we just looked at, that the waves themselves just look very different. They break differently. They have different periods. They have different frequencies, different speeds. And that's something that's important to keep in mind as we're talking about assessing wave energy on a shoreline itself. So talking a little bit more about some of these characteristics of waves and these forces that we get. You have a wave that's formed is going to have a crest and it's going to have a trough. And the waves actually have a circular orbit. So as that energy is getting transferred from the wind to the water, that wave is actually moving in a circular motion. Starts to move again toward the shoreline. You start to get to that breaking point, and then that wave starts to crest up and break over the shoreline itself. And typically where that wave is breaking on the shoreline is our highest energy, and those areas have our highest potential for erosion. So where does that wave height really come from? Well, the wave height most often comes from this combination of fetch, depth, and then that run up. You're going to see things like site orientation really come into play when we're discussing wave height. So typically, if we're in protected bays, or we have even structures like jetties and groins and breakwaters, different structures, be they natural or man-made, are going to affect wave energy. But the reason that they really affect that wave energy is that they cut off the fetch. So some of those very specific structures, by cutting off the fetch, they're going to reduce the fetch, which then is in turn going to reduce that wave energy and ultimately reduce that wave height. So you'll see some sources out there that'll talk a lot about orientation and how important that is. But really, the reason that it's so important is really what that orientation does for reducing or maximizing wave fetch. One thing that's we've observed over time that is important to keep in mind is that some places will say to look at average fetch. We've seen this historically in some different sources. Through experience, we've actually learned that we really focus on that maximum fetch. And I like, in my mind, I kind of call this the one storm theory. And this came from one specific project, actually one that we had worked on with John Hardig at the International Wildlife Refuge quite a few years back. The site was up at the Detroit River, just upstream of Lake Erie. Well, we had just a few degrees of wind that could have caused erosive forces and waves to push from Lake Erie up the Detroit River. Well, we had the exact perfect southeast storm happen shortly after we finished construction of a natural shoreline there, and it caused a fair amount of damage to that site. So even though the probability of that happening was very low, the fact was that the perfect storm with that maximum fetch was able to cause some damage. So we really try to focus on max fetch when we're designing sites. Some of the other things that we look at are adjacent features, be they seawalls, groins, jetties, breakwalls, docks, because all of these different features can either absorb or deflect wave energy. And they can have a very specific influence on the site that you might be looking at working with or trying to protect. So that's part of the reason that we'll say you can't assess wave energy with desktop analysis alone. You always need to go out to a site and look at it and put your own eyes on it, because that's the only way that you can really capture some of those individual site nuances that might be affecting your site. And then in addition to that, we talk a lot about aquatic vegetation. And the reality is that rooted, submergent, and emergent vegetation on a shoreline or in the water itself has an incredible buffering capability against waves. So when we're able to establish vegetation or have areas that are already established, that vegetation will buffer that wave energy. So we talk a lot about shoreline slope, and I kind of touched on that earlier. So we have this idea that waves are going to break over and lose energy when the wave height hits about 80% of the water depth. So what that means is that an 8-inch wave is going to start to break in about 10 inches of water. So what that does, as we watch kind of our surfer dude here go through the gentle, moderate, and steep slopes. So right now you'll see the steep slope. And when that happens, the wave doesn't start to break and create that orbital force until right when it gets up onto the shoreline. The next replay that we have here, what you'll see when you have the gentle shoreline slope, that wave is going to break offshore. And then you're just going to get that swash and backswash happen. So a lot of that orbital force, that energy is actually dissipated as a result of that shoreline. And then with the moderate energy, obviously you get somewhere in between. So the main takeaway here is when we're talking about shoreline protection and wave energy and how those waves actually impact the shoreline, the gentler the slope, for one, the softer we can make the shoreline, but also just the overall less energy that will exist, that will affect the shoreline in the first place. So here's a couple of examples of this actually in action. So the top picture that actually, so wind conditions were very similar on both of these water bodies at the times that these pictures were taken. The one on the top left is Muskegon Lake. This site had about a 4-mile fetch. The deepest part of the lake is about a half a mile from the site, and it's about 60 feet deep. The picture on the lower right is Lake Michigan. And I took that picture on a day when we had about 40 to 50 mile an hour sustained winds. And there were actually 20 foot waves out offshore in Lake Michigan at the time that I took this picture. But you wouldn't necessarily know it from looking at it. Because what you have on the top left is due to a combination of boat activity. And here you have a concrete and steel seawall. Water is much deeper, much closer to that shoreline itself. So even though at this time, this lake only had 6 to 8 foot waves, those waves didn't break and that energy didn't start to dissipate until it hit that seawall itself. And in this particular storm, those waves were throwing aquatic vegetation on rooftops across the street from the seawall. That's how much power and energy there was. But on the lower right, on this Lake Michigan beach, you can see because it's a natural shoreline with much less energy and a much gentler slope, even though we had 20-foot waves on this particular day, and there were actually surfers out there on this day surfing. For some of you that may not know, people actually do surf the Great Lakes. Those waves are breaking out offshore. And here you can see those waves are breaking 20 to 30 feet offshore. And what you're seeing actually interact with the shoreline itself is that swash and backswash. So by the time a 20-foot wave starts to hit our shoreline itself, much of that energy is dissipated. So that's all of these theoretical calculations and properties of waves in action in just a couple of photos. So I'm not going to get into design too much here because I don't want to steal Jen's thunder. She's going to talk a lot about different techniques, especially soft shoreline techniques that we can use for shore protection. But what I do want to show is just how important that slope really is from an engineering standpoint as it comes to shore protection. So this is a graph that came out of an old Army Corps of Engineers shore protection manual. The x-axis is wave height, and that's in feet. And the y-axis that you see here is what they call the critical weight of stone. So that y-axis tells you at what point the wave will be able to move that stone. That's what we mean by critical weight of stone. At what point will that stone move? Now, one of the important points to take away here is that this is a logarithmic scale, and that's important. So then what we have plotted on here is the shoreline slope. And what you can see, and I'll show this a little bit more clearly in a second, is that for the same shoreline, so if we have, for example, a 1.5 foot wave, if that same wave will, on a slope that has a 5-degree slope, can move a 1-pound stone. But that same wave on a slope with a 30-degree slope can move a 10-pound stone. So same wave, 1.5-foot wave, just going from a 5-degree slope to a 30-degree slope. You're talking about a factor of 10 in the size of rock that can resist that wave energy. So there is an incredible amount of wave energy. And this is where this slope is important. And again, I'm going to drive this home over and over again. And that's because we've seen this in practice as far as sites that are resilient to wave energy versus those that are not. So we take that slope and then we start to layer in the effects of water levels. And this is something that's been on a lot of people's minds over the last, especially over the last couple of years as the Great Lakes have risen. And we've seen all of our drowned river mouth lakes, rivers, lacustrine estuaries, a lot of water bodies that are under the influence of the Great Lakes see water levels significantly rise. And what happens when those water levels rise is it brings that body of water much closer to the shoreline itself. So that, by a factor of itself, brings those waves that much closer inland by themselves. But then what happens is as that water level gets higher, because of this fact of where the waves start to break, as that water gets deeper, that means that those waves are going to crest much closer to the shoreline itself. And we see that here at this in this particular body of water. I took this video at high water. Because the water is deeper, those waves aren't cresting and breaking until right when they start to hit that rock. Whereas at lower water, those waves would be breaking further offshore. So when we start to think about designing shore protection and understanding what we can and can't do, we need to understand not only fetch and not only orientation and things like this, but we need to understand water depth specifically at high water, not necessarily under average water conditions, but we need to understand if a lake or river rises, what are those waves then going to do to the shoreline itself? So how does that wave energy actually degrade our shorelines? Well, the one that's obvious is soil erosion. At a certain level and a certain amount of energy, those soil itself or even vegetated is not able to resist that wave energy. But then you also see the actual physical displacement of plants. So this is the reason that when you see, say on a high energy Great Lakes shoreline, you don't often see a lot of aquatic vegetation. And that's because that continual energy just creates too much disturbance and actually physically displaces the plants themselves. And one of the other things that we see is turbidity. And this is something that we don't necessarily talk a lot about. But if you have a water body, especially where you have a continual wave or boat activity and things like that, it makes the water more turbid. And when water becomes more turbid, it reduces or it becomes less habitable for wildlife, and it also starts to limit the diversity and types of submergent vegetation that can exist in that water body because there's less sunlight essentially reaching the lake bed. But then one of the other things that we see, and some of this information came from a great study came out of the Chesapeake Bay, specifically on boats and natural shorelines a couple of years ago. Higher wave energy will lead to armoring, regardless of whether or not they are wind or boat driven. So if we look on the graph here, we see as the maximum fetch goes up in the top and our blue candles here, you will see a higher percentage of the shoreline armored. Intuitively, that makes sense. The more the bigger waves you see, the more armoring people tend to use. But The other thing that you see here is as boating intensity increases, you also see armoring go up. So it really doesn't matter where the waves are coming from. The higher intensity of the waves, the more frequent waves are hitting a shoreline, the more people tend to armor their lake shores. And that then in turn can actually start to snowball on itself, because the more hardened structures you put on a shoreline, the more it deflects that energy, the more you lose aquatic vegetation, and then the bigger your waves get again. So these types of things can really start to snowball on themselves. So the Tip of the Mitt Watershed Council put together some great graphics, and I'm putting in a plug for Jen, who's talking in a little bit here. But these graphics do a great job of really starting to show what happens when waves start to interact with shorelines themselves. So you get this kind of perpetual movement, this constant wave energy interacting with shorelines themselves. And when you don't have vegetation present and you just have loose sediment, those waves are going to continue to churn. And they're going to continue to stir up that sediment, which can lead to that turbidity and also a lack of aquatic vegetation. Then the trouble in this, and as I was mentioning, how waves how this problem starts to multiply on itself, is to abate wave energy, people will often put in sheet piling. What happens when you put in sheet piling, just like that photograph that I showed a little bit further back, is all of that energy has to go somewhere. Again, thinking about waves are just solar powered energy. All of that energy has to go somewhere. Well, when a wave hits a steel vertical surface like a sheet pile wall, that energy gets transferred down into the lake sediment. And what tends to happen in front of sheet piling is that wave energy starts to carve out the lake bottom. What that does is it makes the lake deeper where that sheet piling is, and it also limits the ability of aquatic growth to grow right in front of that lake, or of aquatic vegetation to grow right in front of that sheeting. So you lose your natural means of shoreline protection, which are a gentler slope and aquatic vegetation. So these things multiply on themselves. And then as that water gets deeper, just like that picture that I showed a little while ago, the waves break closer to the shoreline. And the more that steel sheeting that you get, the harder it is to go back from a whole lake perspective. And then if you're in the unenviable situation of wanting to put in a natural shoreline on your property, but having a neighbor who has sheeting or has a vertical seawall of some sort, what happens is, again, all this energy goes somewhere. It goes down and it goes out. And you can see this very commonly as that wave energy transfers laterally along that vertical surface. Eventually, it's going to get released somewhere. And typically that's going to be on the unprotected or unarmored surface that's adjacent to that property itself. So this is where what you see happen, and especially on overpopulated lakes, is one person puts in a seawall that starts to create a problem on their neighbor's property. So that person puts in a seawall, and then that person puts in a seawall. And the next thing you know, you wind up with entire lakes that are virtually all armored, which leads to the severe degradation of the entire ecological community within the lake itself across that land water interface. But when we have our good guy plants to the rescue, plants are able to do several things for us. So for one, in addition to all of the great habitat benefits that we get from having aquatic vegetation, the plant roots themselves will lock in and bind the soil. So it'll hold that sediment in place and it'll keep that sediment from moving. But also the vegetation itself will work to buffer that wave energy. So one of the best examples that I've seen, and there's not a lot of great quantified literature about this, there's a lot of anecdotal information, but Denny Albert out at Oregon State, who actually spoke at the Shoreline in Shallows conference back in 2011, 2012, I think, something like that. He used Oregon State's wave tank, and he took 3 square bulrush, Scenoplectus americanus, and he put it into this wave tank in locked in sediment, and he started hitting it with higher and higher waves in a wave tank because he wanted to see at what point that those rhizomes would start to break up. The reason that he chose that specific plant is that is the only plant that we really find in our highest energy shorelines in the Great Lakes. So you'll find Scenoplectus americanus growing in 4 feet of water in a Lake Superior Bay, big high energy shorelines. So Denny, in this wave tank experiment, he started hitting it with higher and higher and higher waves. What ended up happening is he had these boxes that he had created for his experiment. He got up to about 3 foot high waves and it destroyed his experiment before it destroyed the plants. So all of his boxes started to break and fall apart. He was never able to actually destroy those rhizomes with that experiment. So it was great, quantified data showing us that aquatic vegetation on shorelines really do work. So how do we calculate wave energy? So I'm not going to get into the hard specifics of some of the detailed calculations right now. Again, this is wave energy for non-engineers, but engineers will use what they call hindcasting or various computer models, and utilizing these same types of features such as slope, fetch, water depth, calculated storm wind speeds. They can calculate wave energy from a desktop perspective. One of the tools that I like to use, short of doing the full engineered modeling, is the Wisconsin DNR has come up with this wave energy calculator. And I'll talk more about that in just a second. It's a great, very user-friendly tool using a lot of the same parameters and winds up being fairly accurate for estimating wave energy. Then the other thing that we always want to keep in mind here is using some of those observations. You can't rely solely on anecdotal information, but you also can't rely solely on a desktop analysis either. So the Wisconsin Department of Natural Resources has this online wave energy calculator, and here's a link to that below. This calculator has just 2 inputs. You calculate the fetch from your site, and then you calculate the mean water depth across your site. And then using an assumed storm wind speed of 51.33 feet per second, this online free calculator will give you an estimated wave height. So there may be specific site variables that you need to account for that this specific tool may not be able to account for, but it gives you a great starting point that in about 2 or 3 minutes, if you can calculate your fetch and you can calculate an average depth using basic tools, you can get a pretty good idea from a desktop analysis of what kind of waves might be hitting your shoreline. So this is an example of why I feel like you need to have multiple tools. So this was a demonstration site that we used for the Michigan Natural Shoreline Partnership several years ago. And at the time, Jane Herbert, who was with Michigan State University, wanted me to go out to the site and take a look at it. So I looked at the site, and typically what we do is we do a desktop analysis first, and then we go out to the site to take a look at it. And I looked at this site and I said, well, okay, the fetch is less than a mile, so not very long. And based on the bathymetric information that I had, I calculated wave energy to be very low at the shoreline itself. So what I did is I got out to the site, and we happened to have, so if you look at the orientation of the site here, we happened to have about 40-mile-an-hour southwest winds on the day that I went out to the site. So it was a great conditions to see, what's likely to be about the highest waves that the site's going to kick up. So I get out, so I modeled from a desktop perspective, the waves to be around or less than a foot. So fairly low energy. And I got out to the site and I didn't know exactly where the project was. So I started walking trails. This is a county park. And I got to the location that's over there on the right where that red star is. And I looked at it and I'm out there again, 40 mile an hour southwest winds. And the waves are breaking out offshore. They're barely lapping up along the shoreline. There's all of this aquatic vegetation there, nice, gentle, sandy slope. And I thought to myself, well, where's the project? There's no erosion here. There's nothing going on. Everything's soft. It's protected. The site's fine. So then I start walking along the shoreline a little bit. And I got over to the red star on the left or on the west there, that's just west of that beach. And right there, I observed about 1.5 waves breaking right on the shoreline, even though just about 300 feet to the east, those waves were only about 6 inches. And what had happened is that boats would regularly dock at that location. People would jump off their boats and go get into, and they would use that as a docking location to go visit that beach. So what happened is after years of that, all of that prop wash scoured out a significant hole out in front of that site location, which created water depth that was somewhere between 5 and 8 feet deep. And what that meant is that those waves, instead of breaking offshore, they were breaking right onshore. And instead of a 6-inch wave, we had 1.5 waves, which, going back to our logarithmic scale that we were showing before, there's a significant amount more energy hitting a shoreline when there's a 1.5 wave as opposed to a 6-inch wave. And at that point, I observed about 18-inch high cut actively eroding banks. So this is why you can't rely on desktop analysis alone, that you need to go out and actually physically look at a site, look for things like human use, adjacent structures, those actual very specific site conditions that might affect how waves are interacting with your shoreline itself. So again, not getting into design too much, but as we start to talk about ways that we can design and incorporate natural shorelines as shoreline protection, we take our cues from nature. So I took this picture off the tip of the Leelanau Isle Peninsula, which is way up, wide open fetch, super high energy all the way across Lake Michigan. And there are places in that along that shore where you see nice natural vegetated wetlands. So what we do is we try to take cues from these existing high energy shorelines. What are those physical conditions like that we can then translate to design of natural shoreline protection? And some of the very common characteristics that we see are between 10-on-1 and 20-on-1 slopes. Specifically, when we get up to 15-to-1 to 20-on-1 slopes, that tends to be where we see our coastal wetlands and high energy systems. That tends to be where we see natural beaches on high energy coastal and high energy open types of systems. They're not always vegetated, but they often have some kind of vegetation. You usually see these kind of mosaics of grasses, shrubs, and wildflowers, and you see that these communities are also very transient. They continually change. So just because there's change, it doesn't necessarily mean that it's unstable. And again, these do provide us a template for understanding how to restore our shorelines. So in summary, most often, throughout the Great Lakes, whether it's inland lakes or Great Lakes shorelines themselves, lakes are typically originating from either wind or disturbances, and those disturbances being specifically boats. Fetch depth and wind speed or duration tend to be the key driving factors in wave height and ultimately how that wave interacts with and affects the shoreline itself. Although, again, we also have boats, which Alex is going to talk about a lot more in a minute here. And one of the biggest things that we can take away after monitoring sites that have been in the ground for years and years and years is that these gentler shoreline slopes and vegetation will dampen and dissipate wave energy. So if there's one thing we can do to help soften shorelines, it's create slopes that are as gentle as possible because of all of those physical parameters of the waves themselves. And with that, we'll take some questions.
Great. Thank you, Brian. We have a few questions to answer. Let's see. One question I did answer a little bit already, but there was a question regarding the Wisconsin wave calculator, which has been indicated to show like, okay, well, it doesn't really factor in the wake boat issues. And if a homeowner or somebody was going to be using that, are there other ways to compensate for that? You mentioned, doing site assessment, full assessment, really in order to use multiple tools. But if you're just a landowner, is there a better way to help understand using that tool?
So honestly, it's a big issue that we have right now, is that there is not any kind of easy way to quantify those boat wave impacts. I'm definitely curious to see what Alex has to say next, because perhaps he has a tool that I might not be aware of. But I have not been able to find, and I've talked to a lot of people and tried to look for easy ways to actually quantify that energy. And part of it is that it's human behavior, and human behavior is inherently very unpredictable. So the best way to really understand what's happening on a shoreline is to use your own eyeballs and observe those wave heights. So the physical parameters but what you can do is, if you understand the physical parameters of the shoreline, if you can measure your shoreline slope, if you can understand some of those things, then you can at least understand that if wake boats are kicking up a 2-foot or 3-foot high wave, you can have an understanding maybe of some of those design things that you can do to help mitigate some of that, which Jen is going to talk a little bit about earlier. But I have not found, be it for a homeowner or even from an engineering standpoint, any rapid means or any simplified way of being able to actually calculate that energy.
One thing I'll also mention is that the Shoreline Partnership, we actually just had a discussion with a couple of folks on this kind of topic from a site assessment. And we're hopefully going to be working on this topic and have a little bit better tools available to at least do some visual kind of site assessment to get a better understanding of what's happening at a site with regards to particularly boat wakes or that's happening. Another question is, how much do structures like docks or floating platforms, how much their impact on wave energy?
So docks will tend to cause docks, if they have piers in the ground, they will tend to cause localized scouring. So that even though they might dampen the wave energy itself, it might cause localized scouring, which might then cause displacement of aquatic vegetation. Floating platforms, there are actually a lot of people out there, and I've seen it most commonly used in Florida, but I'm actually seeing people talk about bringing these more commonly to our inland lakes or to our inland freshwater lakes. Is some of those floating platforms can actually work to abate wave energy. So I've seen some people, and I haven't seen it actually done yet, but I've talked to some people that are looking into putting in floating docks or floating temporary protection to abate that wave energy. And what those things can do when they're installed properly is not impact the shoreline or the lake bottom community, but still have that dampening effect on wave energy itself. So I think that we are on the edge of starting to see some more things like that start to happen, if we can work through some of the technical details, because there are some examples across the country where those have been used very effectively and intentionally to reduce wave energy.
Okay, next question. Do you think riprap is as good as vegetation for the shoreline to prevent shoreline erosion?
Ooh, that's a good question.
I think it depends.
It depends.
Anyway.
So riprap, so at a certain point, typically because of the way we have physically modified shorelines, or because of the way we use shorelines, there may be too much energy for vegetation alone to be able to resist. And that is just a reality, is that whether it's very high energy areas, modified shorelines, docks, barges, things like that, vegetation at some point just can't hang on anymore. But at a certain level, specifically at lower energy and things like that, vegetation can be every bit as good and effective as rock itself. And one of the benefits to using vegetation, in addition to all of the ecological benefits that you have, is that vegetation, because plants are living organisms, they can adapt to a changing environment. So we see places, and actually this photograph is an example of that, where as water levels come up and down, the vegetation can change and adapt to those changing physical conditions in ways that rock can't. Typically, if you put a rock in a place, that rock is going to stay in that place, unless it's undersized and a wave moves it around. But vegetation can change and it can move, and we use this term dynamic stability. So there's a lot of situations where vegetation can be as good or better than rock, but not all situations.
Okay, what role can placement of coarse woody habitat, i.e. tree bundles, play in both attenuating waves and helping plants get reestablished in wave-impacted shorelines? And one quick question is, does Michigan have programs promoting coarse woody material? I'll answer that second one. We don't have anything specific promoting that yet. We are working on that aspect of helping to promote that. That's important. I will say in our Shoreline Steward survey, that is one of the questions that comes up as well, that we want people to keep our coarse woody habitat in the lake. So I'll let you answer the first part of it.
And the answer to the first part of it is absolutely. And this is, so we go back to the pure vegetation versus riprap situation, or question that we just had. Well, the reality is that vegetation alone cannot always handle higher wave energy. But when we strategically place things like large woody material, be it root wads, logs, we can strategically place that material to actually provide, what we might think of as a structural way of abating wave energy, while at the same time putting habitat back in for all the reasons that Julia just described. So this is something that we're seeing, grow in popularity in a huge amount. We're seeing a lot of people go that way, pilot projects, all kinds of other types of projects, because it's a way of creating a living shoreline. You can strategically place logs, roots, things like that have the strength to handle waves and or ice. And then when they're placed in the right way, then they create safe spots for vegetation to start to get established. So you dampen that wave energy, you get a plant started, and then what we see oftentimes is that plant can then creep out onto the lake bed, lakeward of those logs. So there's a lot more information coming. I'm not sure if Jen's going to be able to touch on that a little bit when she talks about techniques, but absolutely, we want to use as much wood as we can on shorelines.
Mm-hmm. Is there a difference in wave reflection between a steel seawall, and a large boulder riprap revetment?
Yes. So one of the things that we like to do, if we can't use pure vegetation for any reason we try to use sloped rock when we can. And I know that Jen's going to talk about this a little bit, so I don't want to steal her thunder too much. But what happens is, by having that rougher surface, instead of deflecting that wave energy, you are absorbing and diffusing that wave energy. So having that scattered rock, especially if it can be sloped, it doesn't cause that scouring from waves. Instead, that rock on the slope, it'll deflect and it'll diffract that wave energy. Mm-hmm. So one of the things that we'll say is, if we can't use vegetation alone, sloped rock is still way better than steel.
Yeah, and I will add too, if the rock is placed at a vertical, like a vertical rock wall, then it's really not going to be much different than a steel seawall. So it really it's important that the rock is sloped appropriately. Okay, one last quick question before we switch over to Alex. How does the bottom type of the lake, like sand, gravel, rock along that slope, influence the energy at the shoreline? Is the wave energy?
So that's a really good question, Ralph. And when you're talking about offshore, it doesn't seem to affect it as much. But one of the things that I've actually had some recent conversations over the last few weeks about is there's a reality that we have natural shorelines in the Great Lakes that are not purely sand or purely organic matter. We have natural shorelines that are constructed of cobblestone or limestone and things like that. And those are the natural shorelines that we tend to see in some of our highest energy environments. where that sloped cobblestone, out of 20-on-1, if you think about Lake Superior, northern Lake Michigan, places like that, where you might get 8 or 10-foot waves, you can get natural vegetated shorelines with sloped rock. So when we talk about using natural shorelines as reference communities, sometimes instead of only thinking of wetlands like the one that we have in the picture here, maybe we start to rewire our brains a little bit and start to think about other types of natural communities that we could try to mimic, such as some of those cobblestone shores. So there are probably some technical nuances as far as wave height and friction itself, as far as it affects wave energy, but I'll leave it at that for now.
Okay, fabulous. Now, I know that there are also other questions that have not been answered. We'll try and follow up with them as much as we can in the question and answer through typing. If not, then we will try and answer as many as we can in the follow-up.